Rocket Science. This is Mr. B. We're going to finish up our section on stars today and how they're classified. And for this section, there's a diagram that we're going to take a look at called HR diagrams. And these are used to estimate the sizes of stars and their distances and to infer how they can in fact change over time. So stars can be classified by locating them on a graph showing two easily determined characteristics. Such a graph is called the Hertzsprung-Russell diagram, or to make it much simpler on us, an HR diagram. So an HR diagram, definitely need to write this down, is a graph of the surface temperature or color, because remember they're the same thing with kind of blue, yellow, then red, and absolute brightness of a sample of stars. So we graph them again, the higher surface temperature or color, and we graph them based off of their absolute brightness. The horizontal axis, which again is going to the side, shows the surface, again going across there, shows the surface temperature of the stars. Again, a star's color is directly related to its surface temperature. Again, blue stars are going to be warmer, followed then I think they're going to have some white stars, then yellow, then red. The hottest blue stars are on the left and the coolest red stars are on the right, and they can range anywhere from less than 3,000 Kelvin to more than 30,000 Kelvin on the surface. So that's the horizontal axis going side to side. The vertical axis is the of the HR diagram, shows the absolute brightness with the brightest stars at the top and the faintest at the bottom. So the absolute brightness of stars vary even more than the temperature. So there's a lot of difference here from brightnesses. There's some stars with an absolute brightness that is 1/10,000th of the sun, meaning take the sun, divide it by 10,000, so it's much less than the sun in its absolute brightness. And then there are stars that are more than 1,000,000 times brighter than the sun. So take the absolute brightness of the sun, times that by 1,000,000, and you have some of the other stars there. So absolute brightness varies greatly. Again, temperature varies greatly as well, but absolute brightness definitely varies much more. So here's kind of what this diagram looks like. So the hottest, brightest star would be right here in the top left. Again, they don't really have this one labeled, but this would be our hottest, brightest star. Toward this would be our coolest, dimmest star right down here at the bottom. So going from up and down, again, so all of these stars at the top are the brightest overall, and then but all these stars over here in the blue are much more warmer. So Sirius B is much, again, has less absolute brightness, but then let's say Betelgeuse, because again, Betelgeuse is much brighter. We can see it. However, Betelgeuse is much cooler because it is in the red temperature range there. So you kind of have to look at two different factors there. Again, I might print this out and have us practice with a little bit or put it up on the board so we can see that. But just to give you an idea of where our sun is, our sun's right smack here in the center. We said at the beginning that the sun is a very average star, and that's kind of true and kind of visible in this graph. It's almost like in the dead center, like in between. Again, it has similar amounts to the left, similar amounts to the right, similar amounts above, similar amounts below. So again, it's not overly hot, it's not the hottest, but it's definitely not the coldest. It's not the dimmest, but it's definitely not the brightest either. So the sun kind of falls right in the middle of what's called a main sequence there. And the main sequence is the fact that kind of something we've kind of noticed, that stars only occur in certain places on the HR diagram. Most of the stars are found along a diagonal band. Oh, excuse me. Running from the bright, hot stars on the upper left to the dim, cool stars on the lower right. And the astronomers call this diagonal band on the HR diagram the main sequence. About 90% of all stars are found on this main sequence, and again, the sun is lying near the middle of this band, so kind of giving an idea that the sun is kind of an average star. Again, that average star is just perfect for us in sustaining our life, though. So again, 90% of all stars are found on this main sequence. Again, go back right here. So again, you can see most of them are falling in this main sequence band. Again, we have some giants, some super giants, and some white dwarfs. They're going to kind of fall off of that band. We're going to talk about some characteristics of why they are not in that main sequence. So in general, talking about giants and dwarfs here, there are two factors that determine a star's absolute brightness: its size and its surface temperature. Again, the HR diagram shows the star's absolute brightness and its surface temperature. If you compare two stars at the same temperature, the brighter one must be larger. So that just kind of makes sense. Again, you have two stars, they're the same temperature. If one appears brighter than the other, or if the one has an absolute brightness higher than the other, then it has to be larger because it's based off of the mass as well. Um, hotter stars are brighter than cooler stars of the same size. So again, if there's two stars, if they're the exact same size, and we can see that one's brightness is less than the other, we can assume the less bright one is cooler than the more bright one. So can just kind of making some kind of comparisons there on what that graph is showing us. And so based off of that, the very bright stars that we see in the upper right of the HR diagram, those are called supergiants. Supergiants are much brighter than the main sequence stars of the same temperature, so they must be very large compared with the main sequence stars. So again, they're much brighter. I'm just going to say if we can go back here really quickly. So we have our supergiants right here. Again, they are much brighter than the one. So again, brightness up at the top. You can see these are all at the top. These two blue supergiants are again kind of close to that one, but again above the main sequence star. So they are brighter, so therefore they must be bigger. Again, same with these white ones. Higher absolute brightness, so they are bigger than the main sequence. Polaris, higher absolute brightness, which means it's bigger than our other yellow stars right here. Again, Betelgeuse and Taurus, again, red supergiants here, again, bigger than any of them in the main sequence there. So, again, those are called our supergiants. Again, they're very large. And then they can range in size from 100 to 1,000 times the diameter of our sun, so they get very large. And just below the supergiants on the HR diagram are the giants. Again, they're large, bright stars that are smaller and fainter than the supergiants, but still quite large. And then below the main sequence, we have what are called white dwarfs. White dwarfs are small, dense remains of low or medium mass stars. They are hot, but they are dimmer than main sequence stars at the same temperature, again, based off of the fact that they are much smaller, which means that they are going to be much dimmer than the main sequence stars. So here's a picture that kind of gives a comparison between a white dwarf and our sun and like a red giant. So right here, we have a little tiny white dwarf, which is, let's see, that the sun is, so this red giant is 1,000 times that of the white dwarf, and then it is 10 to 100 times greater than the sun. So this red giant, you can't fit on the screen, but this just gives you a comparison of just part of how massive a red giant is compared to the size of our sun compared to the white dwarf there. There actually is an interesting video that kind of compares the sizes of different things. I might have to find that for you guys here, but that's it for our stars section. Let me know if you have any questions.